Hi everyone, this is a very interesting topic as we are going to see about Fibonacci numbers and how nature involves in it. This video has two segments. In the first segment, we are going to look at the Fibonacci numbers and golden ratio and why they appear in various family trees. Secondly, examines how the golden section is used by nature in some detail, including growing plants, famous arts, historical buildings, music, logos, and there are so many applications. Let's look first at the rabbit puzzle that Fibonacci wrote about it. This introduces you to the Fibonacci number series in an earlier stage and the simple definition of the whole never-ending series. The original problem that Fibonacci investigated was about how fast rabbits could breed in ideal circumstances. Suppose a newly born pair of rabbits, one male, one female, are put in a field. Rabbits are able to mate at the age of 1 month so that at the end of its second month, a female can produce another pair of rabbits. Suppose that our rabbits never die and that the female always produces one new pair every month from the second month on. The puzzle that Fibonacci posted was, how many pairs will there be in 1 year? As we look at this problem, it will take more time to calculate. So he finds the secret concept behind this problem. See this picture. At the end of the first month, they mate, but there is still only one pair. At the end of the second month, the female produces a new pair. So now there are two pairs of rabbits in the field. At the end of the third month, the original female produces a second pair, making three pairs in all in the field. At the end of the fourth month, the original female has produced yet another new pair. The female born 2 months ago produces her first pair also, making 5 pairs. So we get the number of pairs of rabbits in the field at the start of each month is 1, 1, 2, 3, 5, 8, 13, 21, 34 like this. So we can easily say that each number in the Fibonacci series is the sum of the preceding two numbers. Next we are going to see what is golden ratio. If we take the ratio of two successive numbers in Fibonacci series and we divide each by the number before it, we will find the following series of numbers. Like second number in the series is 1. First number is 1. 1 divided by 1 equal to 1. Third number is 2. Second number is 1. 2 divided by 1 equal to 2. Fourth number is 3. Third number is 2. So 3 divided by 2 equal to 1.5. Like this it goes on. The important thing we are noticing here is after fourth ratio all the numbers are seem similar. So it is easier to see what is happening if we plot the ratios on a graph. The numerator numbers are taken as I in the x-axis. The answers which means the ratios are taken as phi in the y-axis. So if we plot the coordinates like 1, 1, 2, 2, 3, 1.5, 5, 1.67, 13, 1.625, 21, 1.615. So this graphs is like that. The ratio seems to be settling down to a particular value, which we call the golden ratio or the golden number. It has a value of approximately 1.618034. The golden ratio 1.618034 is also called an golden section or the golden mean or just the golden number. It is often represented by a Greek letter phi. So phi is approximately 1.618034. Next we define the function of this sequence like we know nth term is the sum of two preceding terms, that is n minus 1th term and n minus 2th term. For n greater than 2, fn equal to fn minus 1 plus fn minus 2. So this function gives us the following sequence. This is called Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, 21, etc. We can make another picture showing the Fibonacci numbers. If we start with two small squares of size 1 next to each other. In the below of both of these squares, draw a square of size 2, that is 1 plus 1. We can now draw a new square touching both a unit square and the latest square of size 2. So having sides 3 units long. And then another touching both the 2 square and the 3 square, which has the side of 5 units. We can continue adding squares around the picture, each new square having a side which is as long as the sum of the latest 2 squares' sides. This set of rectangles are called Fibonacci rectangles. Here is a spiral drawn in the squares, a quarter of a circle in each square. Such spirals are seen in the shape of shells of snails and seashells, and as we see later, in the arrangement of seeds on flowering plants too. The spiral in the squares makes a line from the center of the spiral increased by a factor of the golden number in each square. So points on the spiral are 1.618 times as far from the center after a quarter turn. In a whole turn, the points on a radius out from the center are 1.618 whole power 4. That is 6.854. So this is a whole concept of Fibonacci rectangles and shell spirals. So in the second part, we are going to see some interesting applications in Fibonacci numbers and golden ratios. It will be mind-blowing things. First one is tree branches in Fibonacci pattern. So plant in particular shows the Fibonacci numbers in the number of growing points that it has. Suppose that when a plant puts out a new shoot, that shoot has to grow 2 months before it is strong enough to support branching. If it branches every month after that at the growing point, we get the picture shown here. A plant that grows very much like this is a sneezewort. So this is an example of this pattern. So second example is on many plants the number of petals is a Fibonacci number. For example, buttercups have 5 petals, lilies and iris have 3 petals, and some flowers have 8, 13, 21, 34, 55, 89. Like this Fibonacci numbers. But very few plants show 4 petals. Like 4 is not a Fibonacci number. So third beautiful example is Parthenon in Greece. As we know earlier, many buildings and artworks have the golden ratio in them. An example would be the Parthenon in Greece. Golden spiral supremost on the Parthenon building in Greece, but there is no evidence that the golden ratio played a role in the design of this building. It is present in geometry. Here we can see the image of this spiral supremost on the Parthenon in Greece. Fourth one is Leonardo da Vinci's artwork. One very famous piece known as Mona Lisa, painted by Leonardo da Vinci, is drawn according to the golden ratio. Actually, the golden proportion can be found throughout the human body. The Mona Lisa has many golden rectangles throughout the painting. By drawing a rectangle around her face, we can see that it is indeed golden. If we divide that rectangle with a line drawn across her eyes, we get another golden rectangle, meaning that the proportion of her head length to her eyes is golden. There are other golden rectangles that can be drawn on the rest of her body, like from her neck to the top of her hands. Da Vinci created other pieces that were also drawn according to the golden ratio, such as the Last Supper, Old Man and the Vitruvian Man. So next example is Da Vinci's most famous art, the Vitruvian Man. The Vitruvian Man or man in action is the meaning of the Vitruvian Man. Is the drawing of a man inscribed in a circle. The height of the man is in golden proportion from the top of his head to the navel and from his navel to the bottom of his feet. The Vitruvian Man illustrates all of the divine proportions within the human being. Sixth one is, in our body, the ratio of hand to forearm approximates the golden ratio. So we can see this in picture 1:1.618. So this is nothing but golden ratio. Seventh example is violin Fibonacci segments. In a violin, we can see three segments or three ratios which shows golden ratio. So neckboard of the instrument to neckboard on the instrument, that is B1 is to B2. Second one, open strings to remaining portion of unstringed instrument, that is C1 is to C2. And then unboarded neck to body of the instrument, that is A1 is to A2. So these three ratios are golden ratio. Also in music, in a scale dominant note is the fifth note of major scale, which is also the eighth note of all 13 notes that comprise octave. This provides an added instance of Fibonacci numbers in key musical relationship. Interestingly, 8 by 13 is 0.61538, which approximates 5. Eighth example is C heads and leaf arrangements. So this is a larger sunflower with 89 and 55 spirals at the edge. The same happens in many seed and flower heads in nature. The reason seems to be that this arrangement forms an optimal packing of the seeds so that no matter how large the seed head, they are uniformly packed at any stage, all the seeds being the same size. No crowding in the center and not too sparse at the edges. The spirals are patterns that the eye sees. Curvier spirals appearing near the center, flatter spirals appearing the farther out we go. Next one, leaf arrangements. So the Fibonacci numbers occur when counting both the number of times we go around the stem, going from leaf to leaf, as well as counting the leaves we meet until we encounter a leaf directly above the starting one. If we count in the other direction, we get a different number of turns for the same number of leaves. The number of turns in each direction and the number of leaves met are three consecutive Fibonacci numbers. The leaves here are numbered in turn, each exactly 0.618 of a clockwise turn, 222.5 degree from the previous one. So this ratio is called golden ratio and this degree is known as, that is 222.5 degree is known as golden angle. So next example is Great Pyramid of Giza. So this shows golden ratio concept. The height of this pyramid is 481.4 meters and base is 377.9 meters. So if we make this as right angled triangle by Pythagoras theorem, the hypotenuse will be 612.01 meters. We can calculate this by using Pythagoras theorem. When we divide hypotenuse by base, we get golden ratio approximately 1.61950. So 10th example is golden ratio in galaxy. Our galaxy clearly shows how golden ratio forms by golden triangles, as we can see this image. So the last example is logos. So our logos is in the golden ratio. The famous logos in our daily product like Twitter, Apple, Pepsi and many more applications have the logos by using of golden ratio. So finally, I would like to tell you that the golden ratio related not only to aspects of mathematics but also to physics, chemistry, biology and the topology of space-time. So make use of this video to understand how deep our life is related to mathematics. Thank you.